Good morning, everyone. Welcome back to this GIAN course. Today, we're going to be talking about deep learning. So far, we've been looking at some computer vision basics, specifically those basics relevant to metrology. And many of the techniques that we looked at so far, they've been well established for a while. Of course, there's been more productization of those techniques into commercially available products, which are now used widespread, various industries, and it's slowly becoming more commonplace even in some of the applications that we might be interested in as civil engineers. Now, today we'll be looking at deep learning. Of course, deep learning has, since 2012, is really exponentially grown and morphed into modern day AI systems. But of course, the origin of deep learning also comes from traditional AI, which typically meant anything that, any system that tried to mimic human intelligence. So, to give you a brief history, there have been a lot of advances in computer vision that propelled the advances in AI. It started off as a project, as a summer project at MIT, several decades ago. And since then, there's been continuous growth. With the deep learning, we are interested in trying to automatically understand what's happening in an image using some sort of ground truth data. Okay, so let's get into how some different kinds of ways we can extract useful information with deep learning. So here I have 4 common types of methods that can be achieved using deep learning. So we have semantic segmentation. We've spoken about that already, where you've classified each pixel in an image. We have classification, and this could also be combined with more fine-grained localization. So with classification, you have a single object or you have a single entity that you're looking for in an image. And then we have object detection, where you're drawing bounding boxes around objects of interest. And you have instant segmentation, which is a combination of object detection and semantic segmentation, where you have individual instances of objects identified. And those instances are also segmented. And so you have masks for those individual objects. So today I want to talk to you about how CNNs work and how to train them. I also give you some examples of modern deep learning architectures. So we'll quickly look at the transformer mechanism also. The transformer is the basic building block for modern AI systems, including GPT, which stands for a generative pre-trained transformer. We will first look at the basic building blocks of CNNs. We look at the architectures that the early architectures that were invented to get an idea for what are these building blocks and how they fit together. And then I'll show you more architecture examples for classification. And then finally, we'll look at dense prediction architectures. So dense prediction architectures are the kinds that are used for semantic segmentation. With dense prediction, again, you're doing a prediction for every pixel as opposed to a prediction for the whole image. Okay. So I briefly touched upon this sort of intuitive understanding for how CNNs function. And I'll try to elaborate on that a little bit. In this sort of course, I won't have time to go into depth on things, all the details related to how this happens. But I'll still try to give you some intuition, and then you can ask questions if there are things you want more clarity on. Now, if you're trying to deal with a classification problem, your goal is to, if you have an image, right, you want to classify that image into a certain class. So you need to know what classes you are looking for. So say we have crack or no crack as our two classes. Then essentially I want to find a function which takes the image as input and can output some discrete labels where each of those labels correspond to the classes that I'm interested in identifying. So the question is, how do you find this function? The input space to the function is the image. The output space is a integer value. So traditionally, people had built several approaches where you can do a series of processing steps to then arrive at this sort of answer. And to give you a sense for what those methods look like, here I've applied an edge detection filter on this image. So what does an edge detection filter look like? You have, in the edge detection filter, you want high responses where you have an edge, and you want low responses where there's no edge. Now, here in this image, I've inverted that just to make it clearer to see the black crack. So I have low responses where there's an edge and high responses where there's no edge. So what's a simple way to enable such a response? How would you, what computation would you apply on the image to extract an edge? Any ideas? What is the basic idea behind an edge filter? Change in the gradient of pixel. You mean the change in the intensity? Yeah. So the intensity is just the absolute value of the whatever is recorded by the sensor, right? So it can be a 8-bit or it can be a floating point. But if you can find where the intensity is changing a lot, right? You find the regions where the intensity is changing a lot, then those regions are where there's likely going to be an edge. So you can do a convolution operation, right? The way a convolution operation works is you have a sliding window. So if you take a small window, right? So say I zoom into this and I look just at a small window here. I think I can't draw and zoom. Let me unzoom. Say I have a window there. I can take the difference between pixels on the left and pixels on the right, right? And then as I move this window, that difference will spike when there's an edge. So that's the basic idea. So as you move this window along, and then you record that difference, the average of that difference at every point where you move that window. And as you move the window along the whole image, then you get zeros mostly. And you can do more things. That instead of just taking the difference, you can blur it out by applying a Gaussian kernel. So it looks more blurry. So you're averaging out small variations, and only large variations will get highlighted. So there are all those details that you can incorporate into building a more robust edge detector, but that's the basic idea. You have some filter that you are dragging across the image. So the filter is basically this 3x3 kernel, or it can be n by n. It has to be odd numbers. And you can design what these numbers need to be inside the filter. So I can say that I want to take the difference, so I'm going to have these as ones, and I'll have these as negative ones. Okay. Then I take every time I move the filter to a certain spot, I take the dot product of that filter with the part of the image that it is overlapping with. So when I take that dot product, in this case, it's going to be ones multiplied by the pixels on the right, negative ones multiplied by the pixels on the left. You add that up, and then you get a single value, which represents quantity there. So if it's all without any changes in intensity, then it's going to give you what value? 0, right? And otherwise, it'll give you some response. So here I've inverted it, and so say all edges that you detect are cracks. Okay, say we make that assumption. We're looking at a perfectly smooth concrete wall, okay, and we're only taking pictures of the wall. Then we can make an assumption that all edges that we see are cracks. It's an assumption that's rarely true, but say you have such a system, then you can make that assumption. And if you do make that, then can you design a simple algorithm that detects whether or not there's a crack? So what would you do if you want a 0 or 1 output at the end? So my input is an image, and I know that edges are cracks, and I want the output to be a 0 or 1. How would I get to that? You move the window. Yeah. Yeah. So in my extreme case, even if there's one jump, then it's a crack, right? But if you want to make it more sophisticated, then you can do things like, okay, you count the number of jumps and you have some threshold. Okay, if it's more than this many jumps, then there's a crack. So you can have some simple logic to process this image, and then you decide if there's a crack or not. So similar to that, people build many algorithms that are more and more sophisticated. But the problem is that no matter how many kinds of conditions you add, when you go out in the real world, there are so many conditions that are hard to account for. And so it's very difficult to build a very robust method. Okay, you have to have assumptions, and in cases where all of those assumptions are typically valid, then these handcrafted methods work pretty well. Now, with learning systems, you sort of outsource this task of figuring out what the filter is to a learning algorithm. And so what the learning algorithm does is it has this series of filtering operations, and it tries to figure out what are the best filters that I would need in order to produce the result that is provided to this learning algorithm as ground truth. So you have tens or hundreds of thousands of examples, and then it tunes these filters every time it sees an example to try to get the prediction, once the image is taken, of that network to be whatever is in the ground truth. So what do we need to do to go from an image to an output like that? We the idea here is that convolutions are good at extracting important signals. So we can have a series of convolutions of filters that are initially randomly assigned. So these are random values that are input to the filters, and so that will produce a random result. But over time, we can optimize these random values to converge so that we get the result that we're interested in. So that's the function we're trying to learn. Now, of course, if we want to go from an image, which is say n by n, to an output vector, which is say some small number k by 1, then we have to reduce the size, because the filters, when you filter, you can control what the size of the output is to some extent, but it's nominally going to be size similar to the size of the input. So you also need to reduce the size of your features, and what you get after you apply a filter is called a feature, right? So this would be a feature map, and so here I have a bunch of feature maps. And so you get the feature map after you apply a convolution, but that's not changing the size. If you apply many convolutions in parallel, then you will get many feature maps, right? So if I have 4 filters, then I will get 4 feature maps. And the filtering is, we have random weights assigned, but we need to figure out what that is. But it's a linear operation. So in order to be able to learn more expressive functions, we introduce a nonlinearity into this whole architecture. So what is a very simple nonlinear function? Any thoughts on a simple nonlinear function? What? Y? X squared, yeah. Y equals x squared, that's a quadratic. It's a nonlinear function because it's not linear. Other examples of nonlinear functions? What? E power x, tan x, yeah. So all of log x, all of those are valid nonlinearities. In computer vision, a very simple nonlinearity that's used is called a rectified linear unit, or ReLU. And there's a graph of that there. So this function is linear when the input is positive, okay, and it is 0 when the input is negative. So it's a very simple nonlinearity. We're just making negative value 0. But this works very well for computer vision tasks. There are other nonlinearities that are used in deep learning in general, and I'll list a few later. But that is applied so that this f of I function that we're learning has the ability to represent nonlinear functions, right? Because if you only have a series of linear operations, then by the law of association, the output of a series of linear operations is what? Also linear, right? But that severely limits the space of functions that we can learn. So that's why we need nonlinearities. And so we have that. But also what is important is that we go from this n by n to this k by 1. And for that, we need to remove unnecessary information, and we just want to keep whatever we need to make our judgment. In this case, for example, we would just need to know that there's some crack pixels there. But we want a general mechanism that we can adopt for cracks, falling, corrosion, components, for everything that we're interested in, or any kind of semantic information. So the idea is that you apply this general procedure, and the function adapts to that procedure as it learns, so that the features which are learned adapt to whatever general procedure you have to get rid of information to keep the most important information where it needs to be. So what is done typically is something akin to downsampling. There are different ways you can do this. A common way to do this is called pooling, where you first um, have fixed windows, and they can have a certain stride. So I look at this first window, say it's a 2 by 2 window, and then I simply take the maximum value in that 2 by 2 window, and then I go to another 2 by 2 window, which is I skip one and then I go to the other one. So these two 2 by 2 windows, they're adjacent exactly. So it's pixel number 1, 2, pixel number 3 and 4. And here I simply take the max value, right? That max value goes into that pixel. So then I'm getting rid of half the pixels in the x direction, half the pixels in the y direction. So it's a quarter the size of the original. And those are the three main blocks. So I can repeat these things in as many times as I want. Some caveats. There's a lot of details in how to build that sort of architecture, but that's the main idea. So you can have more convolutions, nonlinearities, and downsampling, and then you can eventually produce a vector, right? And then sometimes what is done is you simply have a matrix multiplication with that vector. So if you have a or if you have a k cross, or if you have a n cross m matrix and you want to get to k cross 1, then you can do a couple matrix multiplications and you can arrive at whatever size that you're looking to get. And you need to learn what those matrix multiplications are as well. Now, traditionally in neural networks, which are the precursor to the convolutional neural networks, they're all matrix multiplications. But if I need to do a matrix multiplication, then I need to learn a huge number of parameters, a huge number of, so each of these numbers, within the filter, right, the A, B, C, D, E, F, G, H, I, those 9 numbers, those are called parameters. Why? Because those filter values are what this network is going to learn, right? Everything else is known. I already know what downsampling method I'm applying. I already know what nonlinearity. Those are decisions that the designer of the architecture will make. But what is going to be optimized for are the convolution weights or parameters. So I'm using many words here. I'm using weights, parameters, filter values, my cursor is lagging a little bit. Okay, these all mean the same thing. Weights, parameters, filter values, they all mean the same thing. So when you're using convolutions, you're able to do some processing, but you only have to learn a few parameters, right? Here I'm only having to learn 9 in this case. But if I wanted to do a direct matrix multiplication, where I go from this, I can rewrite the matrix as a vector and say this is 100 by 100, then I would have, and say I want to go to a 2 by 1, okay, then I need to multiply this. I make it into a single vector, and that would be 100 or 10,000, right? Size of 10,000, and I multiply that by 10,000 by 2, right? So 10,000 by 1 times, or 10,000, 2 by 10,000 times 10,000 by 1 will give you a 2 by 1 value. But then I need to be learning 20,000 weights or parameters. But in this case, I only need to learn 9. Okay. So that's why CNNs are used for images, but also for other kinds of data, because they are parameter efficient. Okay. I just want to erase this because I have a couple more things to show you on this slide. Now, when I do have, this direct matrix multiplication where I'm going from 10,000 by 1 to 2 by 1, that's called a fully connected layer because you're doing this full matrix multiplication. Those are still used, but once you bring down the size of your feature, so instead of it being 10,000, if you bring it down to, say, just 1,000 or even smaller, then you have significant parameter savings, and then you can do this full matrix multiplication. These days, even that is not so popular, but there are some cases where it is. And that's called a fully connected layer. And then you get whatever output size it is that you're looking. Now, we need to set up an optimization problem to where we can learn the parameters. And what do we need to have an optimization? Yeah, you need some cost function, also called a loss function, which is what you are trying to optimize. So the optimization function. And typically, we're trying to minimize this function. Trying to find my mouse. There we go. So minimize that. So our goal is to get the prediction of the network to be the same as what is in our ground truth. So if I have some data set label, right, I have each image given a label 0 or 1 based on whether or not it has crack, then I want my FFI to predict the same thing. So we can construct different loss functions to do this. Here is one such loss function. You can see that if my prediction and y are the same thing, then this function will get minimized, and otherwise it will increase. I won't do the math, but you can do that. Once we have the loss function, then how do you minimize your objective function? What can you use to minimize the objective function in general? If you have to find a minima of a function, then what do? You take the derivative and then do what? Set the derivative to 0. Okay. So if I take the derivative of this, set it to 0, then that will minimize it. What should I take the derivative of the objective function with respect to? The parameters, right? Why? Yeah, we should, because we are trying to find the parameters which minimize the objective function. So I want to take the derivative of the objective function with respect to the parameters. So that's what I have here. I have partial j over partial w1. But really I have to do this for all the parameters. Once I find that derivative, then I can update my parameters. How? I move one step in the direction of steepest descent. And I can decide how big that step needs to be. right? I find the derivative that gives me the direction, but I need to decide how far to move along that. So that is determined by this learning rate. Okay, so this learning rate is what is called a hyperparameter. So hyperparameters are those quantities that are chosen the by the engineer that's building the architecture or designing it. So the hyperparameter is not learned, but it is tuned manually or by some process. You can also have an automated process to find what is a good learning rate. But that decides how far you move along that, and then you can update the weights to move closer to the optimum. Now, this function, I've written it here plainly, but you can see that the loss function we're computing somewhere here, but W1 is all the way here, right? And the relationship between J and W1 is a result of this nonlinearity, more convolutions, downsampling, all of those things. So computing this derivative is not so straightforward. It's easy to do with modern packages, but any ideas how you can compute this derivative? So you can do it numerically, but that won't be accurate and it'll be slow. But instead, you can do it, you can get a perfect expression by doing something that you're all, you've all probably studied in high school, which is if you have a product of many functions, or if you have many functions and you want to find the derivative of the composition of these functions with respect to one of the functions, then what do? What? Yeah, we're finding the partial derivative, but how do you find that? You use the chain rule, right? So I can find the derivative of my objective function with respect to this fully connected layer weights, and then I can find fully collected layer weights with respect to the output of the downsampling layer, and so on and so forth. And then eventually I can get to whatever weight I'm interested in. So that's the basic idea. There are more details to how you can do this, and also there are many so even finding this is challenging because these gradients can cause numerical instability, because if they're all smaller than 1, then it becomes very small, and it's all bigger than 1 explodes. So it's called exploding and vanishing gradients. But there are techniques that people have discovered that you can use to prevent that problem. And because of that, you can have deeper and deeper networks, and you can find the derivatives that propagate through these deeper networks. And so that's part of the reason why it's called deep learning, because you can have so many, you can have these series of operations that you're doing, and the networks then become very deep. Okay. Any questions about this? So that's the basic idea. I think some of you are already, or quite a few of you are already familiar with this. So hopefully it's not too boring. But here we can look at how just some illustrations of what I just described. If I have an image and I want to have a fully connected layer, then I'm essentially taking a dot product, right? And I'm producing a small output, or in this, let's assume it's a single output. And so if I take the dot product between two matrices of the same size, then my output will be what? Scalar, right? Two matrices same size, it'll be a scalar. So that's what a fully connected layer would do. And if you need two scalars, then you would have two of these, right? And so on. But instead, we can use convolutions, right? And you can do this in different dimensions. In 1D, the convolutions look like this. I have my kernel. If you're going to be very strict about the definition of a convolution as is described in signal processing, then you need to flip the filter first and then you drag it. But in computer vision, that is sort of omitted. But in any case, you have a signal and then you have your convolution and you have the result. And similarly, you can do this in 2D. I have my kernel, which is the gray transparent square, which is moving across, the image, which is the blue square, and then I have my result, which is the green. Now, you notice this dotted line around the blue square. Why is that? What is the effect of that dotted line on the result? So the values here, those are, yeah, it's called padding, and those are 0 values. Why would we need that? To maintain the size, right? If we want the output, the green square and the blue square to be the same size, then we need this 0 padding. Without that, what is going to happen to the output size? It will reduce, right? Because you're going to start from this corner, and then you will have, 2 fewer steps. And if you have 2 fewer steps, then the size of the output is going to reduce by 2 dimensions in each direction. So by controlling the padding, you can control the size of the output to some extent. And we can also see this in 3D, right? So here, our filter is 3 dimensions. This is also sometimes used for images. If you have multiple channels, then you can have a single kernel going across all those 3 channels. And say it's important to, in your case, to aggregate information across those channels, then this sort of filter might be used. So with a convolution, you can get an output, right, with just a filter. Oh, it's not changing. Maybe my internet is down. Yeah. So you guys didn't see the 3D filter. Okay, so in the previous slide, I was showing you this. That's the 3D convolution that I was talking about. You have 3 layers with the 3 channels of the image, and you can have a single kernel that is learning, or that's filtering that image. Any questions about this? Okay. So the result of that, of course, is that you can save on parameters, so you have a very efficient, parameter efficient mechanism. And the things in the filter are going to be your learned weights, and then the result of applying filter is a feature map. And you can have as many filters as you want, so that's part of the architecture design. And the more features you have, the more feature maps you get. So I already spoke to you about convolution as feature extraction. This is what it was traditionally done. So this is a Gabor filter, which was traditionally used. And what this does is it finds oriented edges, because you can see some high intensity values and low intensity values. So it's like a subtraction, and it can find edges oriented in a certain direction. If you change the direction of that filter, you get edges oriented in another direction. And you can have a bank of K filters. That's, these are traditional methods that were used in computer vision that all identify different features in the image. And similarly, we have many filters that are learned. And the idea is that you don't hand code it, but you automatically learn what these filters need to be. Now, like I said, the spatial resolution of these feature maps is roughly the same as that of the input, depending on how you set the padding. But you can also alter that by changing the stride. So the stride is how many steps. Yes, it's how many steps the filter slides in order to, before doing the next dot product. So if you skip a pixel, then your stride is going to be 2. If you skip 2 pixels, then your stride is 3. And if your stride is 2, then it reduces the dimension by 1 over 2. And if your slide is S, it reduces the dimension by 1 over S. So it's another way you can downsample instead of doing the pooling. And then you apply the ReLU. So now that we have K feature maps here, then you can use the 3D convolution that we spoke about. So you have an F by F by K filter. And if you have L of these, then you will have L feature maps in the next layer. So here is an example. I have these two filters being applied, and then my output volume is 3 by 3 by 2. And why is it 3 by 3 by 2? The stride is 2, right? And you have 2 filters. So the stride is 2, and because the stride is 2, with the padding, that there are 3 computations that it's doing, right? So it's 3 by 3. And you have 2 filters because you have 2 3D operations that are happening. W0 convolved with the input and W1 convolved with the input. So you have 2 filters at the output. Now, in memory, there are efficient ways to do this. GPUs are very efficient at doing matrix multiplications. Convolutions are not exactly matrix multiplications, but you can rewrite a convolution as a matrix multiplication. The way you do that is by expanding out the convolution into something called a Toeplitz matrix. Wait, I'm going to skip this. We can look at some architectures that have been proposed in the past. So this was the first CNN architecture that was proposed by GIAN back in 1998, and we have all the tools we need to understand what's happening here. We have our input, we have convolutions, and you can see that the size of feature maps are 28 by 28, and there are 6 of them. Okay, and then there's some subsampling that they've done, and I think the way they did the subsampling is through average pooling, so they're averaging across the pooling windows that I spoke about. And then they've used the sigmoid or tanh nonlinearities. At the end, they have fully connected layers, so it goes from 120 to 84 to 10, because the data set that they were using was the MNIST digit data set. So this happened at the University of Buffalo. It was a project with the post office to be, or it's a project that was utilized by the post office to be able to recognize street addresses eventually. So it was one of the early applications of computer vision, and this was trained without GPUs. They have some things which are no longer used, like Gaussian connections, but that's the basic architecture here. I spoke to you about the max pooling layer. Here as well, for the pooling layer, you can choose the stride. So if you have a stride of 1 for the pooling, then what's going to be the size of the output? same as the input, right? So you can still have a pooling with size of 1 if you want, but typically you use a stride of 2 for pooling, and you get the max value, and the size of the output is going to be 1 over S, where S is your stride. Now, if you have k input feature maps, then you're still going to have k output feature maps, because pooling is being applied to every feature map. And yeah, so the window is typically size 2 or 3, and we have stride 2. There's some details about the backward pass, which is how the gradients flow through the pooling layers. And essentially, if you're doing a max pooling, the gradient only flows through the maximum value cell, and that's because that's the only thing that's being retained. And so if the non-maximum values change, that does not affect your loss function. So the gradient only flows through max value. So that's the summary of the CNN pipeline that was proposed by LeCun. I think we understand these building blocks. These are different nonlinearities that are used, or variations of the ReLU. You have a leaky ReLU, which is, it has some, it's two linear functions, but they're different linear functions. So you have some coefficient, which still allows some nonlinear values. And then there's an exponential one, which has a smooth curve on the negative side. So, and the pooling can be max or average. I think you guys get the idea. Now, another very important aspect is the loss function that is used. Now, for classification problems, the most common and widely used loss function is the cross entropy with a softmax. So what is a softmax layer? It tries to express the final layer as probabilities. So say I have a 10 class classification problem, then I can design my output to be 10 cross 1. Okay. And in each of those, I am trying to predict the probability that it is that class. So say I have these categories: dog, cat, boat, and bird. Excuse me. Then I want whatever index, if I have a picture of a boat, then I want whatever index boat is at to be the highest probability in my prediction. And then I can take an argmax and figure out what class it is. So for the ground truth, I would design it simply by assigning a value of 1 to the boat class and a 0 to all the other classes. So if boat is my 0, 1, 2, 3, or yeah, 0, 1, 2 is if that's my n equals 2 class, then the value there would be 1 and everything else would be 0. So my output vector would look like that. Okay. And then I can force my network also to predict a probability distribution, right? So what are the criteria for something to be a probability distribution? Sum to 1, and it should be all non-negative, right? And this softmax gives us one way to do that. So I can exponentiate my score function, which is simply also called the raw response. So that is what you get from applying your whole architecture, right? And say my output is of size 10 cross 1. Now these 10 values, they can be any real number, but I want to constrain it to be probability distribution. So I have my WC dot x, which gives me the value for my particular class C. And I can also find the wk.x, which is the value for all the other classes where k ranges from 1 to c. And I can exponentiate each of those quantities, and then I simply take each of the exponentials divided by the sum of all the exponentials. So when I exponentiate it, it will make sure that it's positive, right? And so even if wc.x is negative, that e to the power of that is still going to be positive, and so I can take e to the power of that divided by its sum, and so that gives me my softmax. So now I have this probability distribution because they're all positive, and when I normalize, they're all going to add to 1, because the sum of all of the wk.x's will be the same as the denominator. So that's my softmax layer, and then I use a cross entropy loss, which basically maximizes the probability of the likelihood of my prediction being the same as my counter. So that's what I showed you on the initial slide there. Okay. So that's my cross entropy loss function, which is commonly used, and get through all this. Now, the idea for this is loosely inspired from the human visual cortex that has this hierarchy of features. So that is similar to the hierarchy of features that are being extracted from the several convolutions that you have. And the idea is that the human visual cortex has, a variation in the amount of complexity of the processing that's happening, and the idea is that earlier layers in the CNN will extract simple things like edges or corners, and latter layers will start to aggregate these things depending on what you're trying to determine to further disambiguate. So if you're doing faces, then maybe initially you'll have edges, and then you'll start to get shapes, and then you'll start to get parts of the face like the eyes, nose. So you have features that specialize in those things, and then you'll have a feature that combines all of that. And it may not be exactly like that, but that's the sense of increasing complexity that the latter features will be handled. Okay, so before 2012, most of the top performing methods for many computer vision tasks were all handcrafted techniques, or non-deep learning techniques to be more specific. In 2011, there was this ImageNet classification challenge that is the ILS VRC, which is the ImageNet Large Scale Visual Recognition Challenge. And they released this massive data set, I think of 1 million images that had 1,000 classes. And that helped significantly advance research on being able to do classification. You can see all deep learning methods in blue and non-deep learning methods in green. So prior to 2012, there were non-deep learning methods, but since then, the deep learning methods surpassed human performance as well on this data set. And so this shows that modern deep learning methods are very good at these sorts of problems. If you have a data set, then it can, and you have good labels, then it can do that sort of classification. And so now this data set itself is obsolete for these kinds of challenges, and they're used more for basic tasks. But it was still, it played a major role in being able to advance these architectures. And some of these architectures are still used today. For example, this ResNet, GoogleNet, before, they're still pretty popular even today. So let's look at some. So the reason that this became popular again in 2012 was because of NVIDIA GPUs and CUDA, and also the availability of the data set. Both of those things were key ingredients. And both of those things continue to be important pillars of any AI system, compute and the data availability. So we can see that this is not too far from the LayNet architecture proposed in 1998, right? So the architecture didn't really change too much, but what changed is the ability to have deeper architectures and compute. So here, they were the first to implement it on a GPU, and they have two parallel paths which are both identical. The reason they had that is because they had two GPUs, and so they wanted to have one path on each so they can learn more parameters. And they took a week to train this. You can see the sizes of the filters, right? You have 11 by 11, 5 by 5, 3 by 3, 3 by 3, 3 by 3. And you can understand the dimensions. You have 24 by 24, sorry, 224 by 224. If you have a stride of 4, then what happens to the output size? Divided by 4, 56. But so yeah, so this is 55 by 55, and that's probably because of padding. And you have two of those, and you have 48 of these filters, so you get the size of 48. And similarly, you can do the math here for all of these layers. And at the end, you have these dense layers, which are fully connected layers, right? So it's a full matrix multiplication, and that goes from 128 by 13 by 13. You can find out what that is, to 2048. And then 2048 to again 2048, and then 2048 to 1000. Why 1000? Because this data set has 1000 classes. They did something called dropout regularization. So regularization is a technique that helps prevent overfitting. We'll study what overfitting is in the next lecture. But what dropout is randomly not using some of your filters or some of your cells of your fully connected layers with some probability p. So say you're doing your dot product, right? I'm going to not use one of my filters in that dot product with some probability p. So say with 1/9 probability I'm dropping. That means every time I'm going to be dropping one of the filter values. And why do you want to do that? It's because you want to learn robust representations that are not brittle. So it's possible that the network will learn representations that are specific to certain patterns and certain a combination of patterns and the parts of the architecture. And if you randomly drop some weights every time, then you are trying to make the network robust to that brittle training. And so if it sees new data, it's more likely to perform well. But it may take longer to train because you're dropping some of these things every time. So they introduced that here. Of course, they had more data because they had ImageNet and bigger model than LayNet. And you can see the number of parameters, the number of units. And of course, this is still small in today's parameter sizes. GPT-3, for example, is 175 billion, and the Llama models, the biggest one is 405 billion, and GPT-4, they haven't released it, but maybe people say it's 500 or 600 billion, or maybe a trillion. So things have grown since this time, but for CNNs, these are still the building blocks that are commonly used. This is another way to express the architecture, right? So this is something that you will see if you look at papers or if you look at code. You can understand what's happening with the architecture here. Any questions about that? Yeah. Say that again. Where? You can use them in both. Yeah. I mean, they're mostly used in fully connected layers, right? But you can use them in the convolution. I don't know what they did in this paper, but you can use them in both. So you can see the computation here. So you can see that the computation is more with the convolutions, right? And that's because the same parameters are being multiplied at many points on the network. But if you look at the number of parameters, it's much more for the fully connected layers. So that's the trade-off. So in 2013, for the same challenge, there was this paper by Clarify that had a refinement. But the main interesting thing about their paper is they studied the filter responses to illustrate that hierarchical concept that I was talking about. So here you can see the filter response for layer 1. It's mostly identifying edges, right? It's been getting excited for edges. And you can see the patches from the input image, right? Because this is the first filter, and the first filter is of size 7 by 7, so it's going to be 7 by 7 patches. And you can see they're mostly edges of different orientations that the filter is getting. And if you look at layer 2, you can see some distinct shapes, right, that different filters are specializing in. You can see, this filter here is specializing in circles. This one is specializing in stripes, and this one's specializing in edges, perhaps. So, and here you can see as we progress, different filters are specializing in more identifiable objects, right? So here are all people, and these are all wheels, and so on and so forth. And this, of course, you would expect as you get closer to the end, then it's identifying the whole image class that is of interest. Now, in 2014, the architecture that won second place is a very popular architecture because they had they simplified, and they had a very elegant architecture. So they replaced the large receptor field, so the 7 by 7, 11 by 11, those are large, with smaller 3 by 3 convolutions. So here they only have the 3 by 3 convolutions, and this is more common these days, and you could also have 1 by 1 convolutions. But this was the first paper to reduce it. The idea is that one 7 by 7 convolution layer with k feature maps needs 49 k square weights, but 3 by 3 convolution layers need only 27 k square weights, right? Because 9 times 3 by 3 is 9, 9 times 3 is 27. And they also experimented with 1 by 1, and they went deeper. You can see Alex and here, VGG16 has 16 layers, VGG19 has 19 layers. And you can see also a comparison. It's much bigger in terms of the memory during operation, the parameters. and also the compute. The winner in 2014 was this GoogleNet architecture, and they had a much deeper architecture, and they had different combinations of filter sets. You can see the stem network, where what they do is they aggressively downsample. Here they have a lot of downsampling. You can see that they go from you can see the strides here, they're all 22112, so it reduces from 224 to 28. And then you have these inception modules, which have multiple layers of operations. So you do the initial 1-by-1 convolutions. The idea with the 1-by-1 convolution is you're trying to reduce the number of feature maps, and then you do 3-by-3, 5-by-5 convolutions. Because when you reduce, so when you do a 1-by-1 convolution, right, you are basically, I don't know if I have the slide here. Yeah, when you do the 1-by-1 convolution, you can collapse L filter maps into a single filter map with the minimum cost, because you're simply multiplying it by a single number, right? So it's a very simple operation, and you can reduce but you still have most of that information. So they do these 1-by-1 convolutions first, and then they apply the more expensive operations to save. And then finally, they need to, of course, you need to make sure they're all the same size, and then you can concatenate those outputs, and you get a new set of outputs. And they had many of these layers, and this is where we start getting the problems because of the depth, because the gradients don't propagate. So they had an interesting solution, which is these days not so common, which is to let me just explain it from this figure, because I don't think I have it. They have these auxiliary outputs. So instead of having a single loss function all the way at the end, they have multiple loss functions computed at different parts. And so their idea was that since we're not able to propagate the gradients, we'll just have earlier loss functions. So you have different ways that the gradient can propagate. And that's how they realized this. But since then, there have been some advances. So there's something called batch normalization, which is commonly used to orient the distribution of each of the feature maps so that the vanishing gradient problem doesn't happen. Vanishing gradient is basically when, or exploding gradient is when your gradients become too small or too big. But if you keep them sort of properly, if their statistics are centered, then that allows you to prevent that problem. And so that was something that was introduced in latter variants, and they had more, more changes. So this was the by 2014, it was almost, performance very close to what a human would do with those 1,000 classes. And here are some more articles that you can read about this. Now, we looked at some classification networks. Of course, since those architectures, they are more modern architectures. I'm not going to go into detail about those classification architectures, but I'll just start talking about segmentation architectures, and many of the things are similar, but I'll start talking about segmentation architectures from 2015. With a dense prediction task, you're trying to predict values for each pixel, and you can think of it as a classification, but you're doing a classification for every pixel. Yeah. So you can still use the same loss function. You can use the softmax for each of the pixels, and you use cross entropy loss. But we need our output to now not be a vector, but we need our output to be the same size as our input. So how do you do that? One seminal work that did this efficiently was a fully convolutional network. So as the name suggests, this network has no fully connected layers. It's only convolutions. And the reason for that is because we want an output that is the same size as the input. And we want that to be as efficient as possible. So if you were to do matrix multiplications, then this starts to become very expensive. So the idea behind these networks is that first you downsample, and you need to do that because you need to extract what is important in that image for you to make these classifications. And then you need to use that downsampled information and upsample to get to the size of the output that you're interested in your data set. So how do you upsample in a deep network? There are different ways you can do this. One common way is a transposed convolution. So you can do this with zero padding, or you can do it with dilated convolution. So if you're doing it with zero padding, then you're just adding zeros around the image, and then you're doing this sort of convolution, and you're getting an output that is bigger size than the input. But you can do this with zero padding in between, right? And this is called dilating the input. You can also dilate the filter, which is called an true convolution or a dilated convolution. But it's basically backward strided. So instead of striding where the CNN, or striding where the convolution meets the image, you are dilating the image itself. So this is also called a fractional stride, fractional input stride. So how does the fully convolutional network architecture work? This is the downsampling part of it. You have an image, you have a convolution, you have pooling layers, and you have you know, 5 convolution and pooling, and then you have your 6th and 7th convolution. And here they're denoting the density of the feature map with respect to the original image by this cell. And because you have 5 pooling layers that downsample this image by 2 to the power of 32, and so you need to upsample again 32 times. So one way is to directly do a 32 times upsampling, and that's called FCN32. So in this network, they didn't really use the transposed convolutions or the backward strided convolution. They just did a bilinear upsampling. So it's just what you would do when you resize an image. But also, instead of only upsampling your pool phi, they also took the earlier downsample layers and upsampled them by smaller amounts to reach the same size. So if you look at pool 4, you only need to upsample that 16 times. And similarly, you can use pool 3, you only need to upsample that 8 times. And they applied their loss function on top of these different upsampled outputs, and a combination of those. And you can see that the FCN8s, they perform better than the FCN32s. So the FCN8s have all of these. The FCN32 only has the top one. So why do you think that is? So what's the difference between the FCN32 prediction and the FCN8 prediction? Is like what? Yeah, so it's a lower resolution because you're upsampling 32 times, right? So if you have a very small image you upsample it 32 times, then it's going to look very blurry, versus if you upsample it 8 times, it's going to look less blurry. And that's kind of what you're seeing. It's kind of what you're seeing here. But the FCN8s, you still want to have that blurry representation, because that is giving you better features, but at lower resolution. So if you use the better features at lower resolution and then more primitive features at higher resolution, then that will allow you to do dense prediction tasks better, since dense predictions, you also need precision at the edges, right? Ideally, you want this to be very sharp. And that can only be very sharp if you have retained all of the information at the earlier layers. So for tasks like crack detection, those details are very, very important. And so you want to have architectures that are able to retain that initial resolution. So this is how they combined FCN32, and then they combine the pool 5 with 2 times upsampling, which is the same size as pool 4, and then they just sum those things, and then they 16 times upsample, and they do the same thing for 2 times upsampled pool 5 and pool 3, and that's how they get their FCN8s. Another way to do the upsampling is max unpooling, where you simply assign the values to cells. You remember for the mirror layer where the max was coming from, and then at that same cell in your decoder or in your upsampling branch, you apply that same you apply the max value at that location, and the rest are all just zeros. Okay, so I know that the 5 came from there, so when I'm doing the unpooling, I put the 5 back there, and the rest are zeros. So here the output is sparse, so we still need to do convolution after this to be able to populate all of the cells. And that's what they did in this SegNet architecture, which is a more modern architecture as far as CNNs go. We can see a very symmetric architecture here. You have downsampling, you have upsampling, and what is this part where you have the downsampling is called an encoder, and the part where you have the upsampling, that's called a decoder. You can also have connections across the encoder branch and the decoder branch, and those are important. Again, why are they important? Because you want to retain details from your initial layers as best as you can in your final layers when you're making your prediction. You don't have those details because the feature is looking to extract what is important, but at the cost of resolution. So for classification, it's not so much a problem because your output is so low dimension. You don't really care. But with dense prediction, you care about those border pixels. Another very popular architecture is the UNet, which was proposed for biomedical image segmentation, but is also very popular for cracks. And that's because you have these connections from your encoder branch to your decoder branch to fuse the higher and lower level feature maps. And here what they do is they concatenate and then they predict at the end. So I think we are at 11:15, so maybe I'll pause here. In the next session, I will talk to you guys a little bit more about these architectures, and then we will run a Jupyter notebook of a segformer, which is a transformer for segmentation, for corrosion detection. So I have that. If you guys have a Google account, you should be able to access it. I'll put a link in the WhatsApp when we come back. Any questions? All right. Yes. Yes. Auxiliary class. Yes. Oh, no, they use the ground truth. It's a classification. So you see that they have the same output stems. You see, this is the output here. You see my cursor? And then you see there as well. You see, it looks the same. But there's this extra green because this size might be different a little bit. Same here. Because you can't do the loss function without the ground truth. All right. Other questions? Yes. 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 Here. So this is what they did in their paper. This is not the best way to do things, but this is what they did. So what's your question? Yes. Yes. When you say last, what do you mean? Um, here? Here, pool 5? Okay, pool 5. No, no, it is. So you have pool 5, upsample twice, same size as pool 4, right? So now I have 2x pool 5, which is same size as pool 4. You see my arrow? Okay, you can add those things up. And then you get still same size as pool 4. And then you 2 times upsample that. That becomes same size as pool 3. And then you add that with pool 3. And then you do your convolution. And then you upsample and then you do your convolution. Make sense? Why is it not? So in the unit they're doing a concatenation. I mean, unit was proposed 1 year after, so they're not that different. And unit is doing the unit has a better upsampling procedure. So here they have bilinear upsampling, which is not as good as doing transpose convolutions or unpooling and then convolutions, things like that. So the upsampling is different, and then here they're doing concatenations, right? I think that's the only difference. And also in unit they're doing it. They have the input image size directly coming to the output. So for biomedical images also you have fine features like cracks, and so it works better for images where you have those fine features. Whereas in FCN they're only doing it up to pool 3, right? They're not going all the way to pool 1, which is a simple modification, but I think that concatenation and the upsampling, those are the three differences. The unit came out in, actually they're both, I suppose, just 2015. So, but the FCN, the preprint came out in 2014, unit came out in 2015. I remember because I was in grad school at the time, and we were testing these things. Okay. Other questions? Yes, yes, yes. I will. Let's. I just have not had time. I'm sorry, but I need to do that. Maybe we can. Do you guys want it before the next session? Yes. Okay. So we'll come back. I'll come back quickly, and I'll do that. Um, or we'll start it a little bit late, so I can send you the slides. I think it's probably worth it. Okay. Uh, we're already at 11:25. So let's pause here, and then we can come back after a break.